I said it before and I will say it again. 2025 will be the year of Edge AI. And I think it's appropriate that this very special episode of the IoT Show is sponsored by the Edge AI Foundation, so formerly known as the TinyML Foundation. The Edge AI Foundation is a place for global innovation, collaboration, advocacy, and education. Anything AI at the edge, they will help and promote. One thing they do have is what they call labs. Collaboration between experts of various domains is possible through these labs. One of the areas of the labs is about huge data sets, a lot of data that scientists, data scientists, or software developer or embedded developer can go play with. And during the last event, the Edge AI Foundation put together a contest, and different experts were able to go play with one of these datasets. Today, we have Samy, one of the contestants, one of the winners, who is here on the IoT Show to tell us everything about his project and how he optimized the dataset and the models for the edge. Once again, thanks for watching, and if you like this episode, don't forget to not only subscribe to the channel, but also like the video and give us a comment, ask your questions. Hi everyone, this is the IoT Show. I'm Olivier, your host. Today we'll talk IoT, but we'll also talk Edge AI. And for that, we have Samy. Samy went through a challenge with the Edge AI Foundation recently and was one of the winners. So we'll talk about this challenge. And Samy, how are you?
Yeah, I'm doing good. How about you?
I'm great. Samy, tell us, where are you based? Where are you calling from?
Yeah, I'm from Bangalore, India.
Oh, must be pretty late for you. It's early for me, but it's late for you, right?
Yeah, it's about like 7:30 p.m. in India now.
Okay. Well, thanks for your time. Thanks for doing this. Tell us about yourself. Who are you? What are you doing?
Yeah, first of all, thank you so much for inviting me for this IoT show. So I have been following your YouTube channel. So I found all those videos are excellent. I really like that idea of having a interview like this where you are inviting experts from different industries and academia, having face-to-face interactions, which is more engaging compared to like doing a lecture style or some technical talk. Okay, so I really appreciate that. So my name is Pandarasamy Arjunan. So people call me Samy. So I am an assistant professor at the Indian Institute of Science. And so I have over 15 years of experience in IoT space. So during my PhD, I started with designing IoT middleware system for smart buildings. So as you know, so in buildings, we have a lot of building management systems and a lot of applications out there, right? So most of the commercial building management systems are like they are very closed in nature. So they provide no or less flexibility. Let's say if you wanted to integrate your own sensors into the system, right? So that's why we decided to design a new IoT middleware architecture, so using which it's also open source architecture. So where you can put your own sensors, and there's a software stack for managing the sensor, collecting sensor data, writing applications on top of this middleware, so that you can really make your building smarter, right? So we, in fact, did multiple deployments in one of our like a testbed buildings. So we focused on multiple applications like object detection, like human occupancy detection, occupancy tracking, so monitoring indoor environmental like a temperature, humidity, so that based on that you can do a smart control to the HVAC systems and lighting system automation. So all those things we did. Okay, and then what happened is that, and then I shifted my focus to IoT analytics. So rather just connecting all these devices, I wanted to apply some of this AML techniques to this IoT sensor data, so that even we can develop even more like interesting use cases and applications. Okay, so I focused on like using smart electricity meter data, and we collect like a high resolution smart meter data, and then I used various machine learning techniques, and these techniques or these models will monitor the energy usage of a building, and it will detect any outliers. So outliers can be like any anomaly usage, so that we can minimize the energy usage or any wastage in a building. Okay, and then currently I'm focusing on Edge AI and AIoT. So AIoT is like artificial intelligence of things. So we are going to put so much AI into all those IoT devices. Okay,
Yeah.
so that's about me.
Awesome. Awesome. Great description. So suffice to say, you know a thing or two about IoT. I think smart buildings is a great use case or series of use case for Edge AI. And as you described, you came to add AI naturally in the scenarios, people counting, detection of presence in a room, this kind of things. Definitely you brought AI to these solutions because it was needed. And interestingly, though, in smart building, very often you have an infrastructure, you have servers, you have heavier, hefty servers that can run, bigger AI, I would say. But you came into working on edge AI, which is something we're going to cover today, and that went through your experience, but also through that challenge that the Edge AI Foundation put together. Can you tell us a little bit about this challenge that you went through?
Yeah, sure. So first of all, I would like to thank you, the HAI community, so that the host who hosted this interesting competition. So the competition is, it's all about developing efficient and tiny machine learning models so that can run in ultra low power microcontrollers. Okay. So the task at hand was, okay, so you have to design an efficient deep learning architecture so that can detect a single task. So the task is, so it has to detect, okay, whether a person is there in the camera, in an image or not. Okay. So you can think of an so this is a fundamental problem. Okay, this is actually, if you ask any AI person, this is a typical like a image classification problem. So people have proposed various architectures like no. So the classical architectures like AlexNet, and then people propose more efficient model architectures like a mobile net, and so many, like dozens of architectures are available. The problem with these architectures are that the problem with all these models are that, so they are very huge, they are bulky, right? So we cannot deploy these models into a microcontroller, so in which we'll have like few kilobytes of memory, and the compute cycles are also very limited. We'll have few megabytes of clock speed. So it's very difficult, it's close to impossible to deploy all these models into this microcontroller. So this is
Yeah.
where the focus of this competition is actually how to design a more efficient, tiny, models so that we can deploy these models into this kind of microcontrollers. So I would like to give you an use case of where this kind of models will be used. Okay, so imagine you have a smart doorbell camera. I think there are some commercial products are available. So the way it works is actually, so the camera is going to continue record the video frames. So
Mhm.
whenever it's able to detect some visitor or some guest, so it's going to alert the owner. Okay,
Okay.
so consider this is an interesting IoT product. So within that, we have to run, all these bulky models, which is not possible, right? So this is where, Edge AI comes into picture. So where the focus will be on, designing more efficient models. So with a very, so efficient, when I say efficient in terms of memory usage, the storage and compute cycles. So all these
Got it.
things should be efficient, as well as we also have to focus on the energy efficiency. So imagine this a doorbell you are going to install, using a battery, right? So they are not going to get continuous power supply. So this model also should be efficient. It should not take too much battery, right? So that's also a fact.
Yep. So a big task at hand, because definitely
Right.
these big models, we talk a lot about large language models for generative AI. We have big vision AI models, and people know about YOLO and others. These are pretty impressive in what they can do, but very often your machine that is running them gets hot real fast. So that means it burns a lot of energy. So what you describe is definitely the context for running AI at the edge. So what is the common methods or techniques to optimize AI at the edge? Can you tell me in a nutshell, high level, what are the things that you can do to make these models that are generic or generalized, I would say, that require a lot of compute, run on tinier devices like microcontrollers?
Yes, sure. I'll be happy to share that. So overall, like broadly, we can classify those techniques into two categories. So the ones which are focused on like a hardware systems. So basically, you can design an efficient AI chip so that can be integrated into all the smart devices. So most of the people from hardware background, they'll be working on all this efficient AI chips. Okay,
Mhm.
and so the other one is actually focused on more on the software side. Basically, you have to design and optimize the software frameworks or the models, so using which you can deploy or create a smaller models. So on the software side, in fact, the focus of this competition is all about designing an efficient software oriented solution to solve this problem. Okay, so under software oriented approaches, we have like a various techniques are available. So one of the widely used techniques is called quantization. So basically, the focus will be on you have to use less number of bits to represent the model's parameters. Okay. So for example, in ChatGPT and all these LLMs, so we are talking about like a billions and trillions of parameters. Okay. So these
Yeah.
parameters, each parameters is going to take some memory, right? So typically they'll be using a float 32-bit data type. So that's like 4 bytes, right? So now with when you consider like a bulky models, when you use like a millions of parameters, so they are not going to fit into the microcontroller, right? So the focus of quantization will be, can we reduce the precision of the weights used in these models so that we can store these models in a compact manner, and during the runtime this model can be decompressed and it can be executed, right? So that's
Yeah.
about quantization. So there are other techniques like a model pruning. So the pruning, the focus will be on reducing the structure of the network. Okay, so typically in a deep neural network we'll have a lot of like neurons and their connections. So they are called the synapses. Okay, now typically in a typical neural network we'll have a lot of such connections into neuron. So can we carefully analyze these neurons and their importance as part of this model's classification or the task? Now, can we systematically, strategically remove those neurons, which is not that much important as part of this network, so that we can shrink this network, right? So that's about pruning. Now, these are like a widely used techniques. So a lot of industries like Nvidia, Sony, Intel, they are developing a lot of frameworks to solve this problem. Okay, provide techniques for implementing all these techniques. So whereas a lot of other advanced techniques are also available, like network architecture search. So where you are going to provide the specification of your hardware or the deployment system, and you are going to use an AI to come up with the efficient model. So that's even more industry, right? So those kind of
Yeah.
advanced techniques are available, but they are not practically usable at this stage. So in fact, as part of these competitions, the baseline model that they have provided and asked to challenge that model is actually designed by an AI system. So that's called collabness. It's called collaborative network architecture search. So they already found out, okay, this is the efficient model. And then they challenge us to know, can you beat this one and come up with even a better model for this? So that's the interesting part of this competition.
Good. Nice, nice. That was a bit like beat the machine as a human.
Yeah, exactly.
Building another machine to beat the machine. I like that. So,
Exactly.
well, interesting description of the different methods. I like this way of presenting, hardware part and software part. It makes sense. But even on the software part, it seems like, even though models are, AI models, and today lots of them are using neural networks, the way you're going to optimize them, is it fair to say that there's no one size fits all, and that you need to look at your use case and what the model is for? Like typically, you would not optimize the same way a vision AI model, the way you would optimize a model that is looking at, for example, vibration data to detect an anomaly, right?
Yeah, you are absolutely right. So there is no one size fit all for this context, right? So there are various use cases like AGI use cases. So the type of model optimization techniques that you use, and all those modeling challenges. So all those things are going to be different. For example, the smart doorbell example that we just described. So that the kind of requirements will be different, because the kind of hardware platform, the microcontroller being used in this control is going to be different. So whereas if you compare a like autonomous car, so where the maybe you want to have like a even more efficient, robust techniques, and it has to process like a really high definition video frames. So so basically based on the context and the requirement by different applications, you have to choose a combination of this technique so that you can optimize these models.
Makes sense. Good segue to my next question. So, back to the challenge itself. What were your techniques and your approach to beat the machine in that challenge? Tell me about what you did.
So the initial, like the baseline model that they have provided consists of like a 6 layers with a different filter size for different layers. So first, I carefully analyze these layers, and what is their importance of modeling or capturing the features from the input image. So I found out there are some discrepancies in this order of these layers and the number of filters used by these layers. So I decided to reduce the last 3 layers into 2 layers so that we can reduce the model complexity and the model size. And by doing that, so there may be problems, so because the model may not be sufficient to capture all the features which is required to identify whether a person is there in the input image or not. To compensate that, what I did is actually, so in the baseline model, the input image size is actually 50 by 50 pixels in size, which is very small. So I thought of increasing it so that you will have like a more information that will be available, and that can be captured by this 5 layers that I have custom designed. Okay, So that's
Okay.
one approach related to the structure of the network. Basically, I completely changed the structure of this network. So instead of five layers, I kind of condense them into sorry, instead of six layers, I condense them into five layers, and then I increase the input image size to slightly larger so that it can capture all those information. And there is
Yeah.
also another reason behind this. Okay, so the number of filters already available in the baseline model is they're not following some standards. Okay, so also we have to make this model hardware friendly. So the hardware friendly, so the number of filters should be order of like to 8, right? It's like 8, 16, 24, so on and so forth.
Yeah.
So but
Yeah.
that was not the case. So I found some of these discrepancies, and I carefully designed the architectures, the layers of these architectures, and made it work. Okay, so this
Right.
is related to the structure of the network. And then I also did some tweak when I was training this network. Okay, so by the way, they have provided 1.3 million training samples, so on which we had to train this network. That's a lot. Okay, so we need
That's a lot of data.
GPUs.
Yeah.
Yeah, so we need a lot of GPUs to train this network. So what I did is actually during the model training, there is something called this, quantization. Just now we discussed, right? So generally,
Yeah.
this is called the post-training quantization. So after you train the network, you apply this quantization techniques to reduce the model size and other parameters. So during the post-training quantization stage, after generally, after you quantize the models, the weights are going to get reduced. Okay, so the precision of these weights are going to get reduced. To compensate that, there is something called this representative data set. So you have to use some another subset of samples to fine tune this weights. So in that case, I use like slightly large number of samples so that the loss incurred by this quantization can be compensated by using like more training samples to adjust these weights. So all these combination of things resulted in a best model architecture. So I ended up with getting the highest accuracy score on that test data set, which is unknown to us. So okay, when we are participating in this competition.
Okay.
Okay, so in terms of memory and storage and MAC, which is called multiply and arithmetic operations, so number of operations required to run these models, which is relatively small compared to the baseline one. I don't have the exact number, but it's relatively small.
Yeah, smart, smart. So you worked on the actual architecture of the neural network, optimizing its size, and then you work on a better way of quantizing, the model that really highlights the fact that there's no one size fits all, right? There's no
Right.
one way, because you
Mhm.
you looked at the actual scenario, and you were talking about, for example, working on the resolution of the images. So that implies that you are working out of images, and not all AI models are about vision AI. And so
Exactly.
you definitely approach that with that in mind. That's great. And you also worked from something, right? You had a base model. And
Right.
is that common? Actually, is that something that, we hear a lot about these open source models that are out there, like YOLO and others, especially for Vision AI. Is that a common way of doing? You start from something which is out there and you really work on optimizing for your edge AI scenario.
Yeah, that's very common, and because we have hundreds or even millions of models or all models are available in the public domain.
Yeah.
People have already designed these networks and they have trained these networks. So it's a very common practice to use existing models and make it efficient and fit into that. But there is a catch. So the catch is actually sometimes these models may not be suitable or they may not be sufficient to capture the subject that you wanted to capture, right? So, for example, let's say you have the YOLO model that you are talking about, right? So it's an example of object detection model. Let's say it's able to detect like 100 different objects. Okay. Now, if you wanted to detect one more object, in that case, you have to take this model. You have to like collect some samples specific to that new object that you wanted to detect, and then you have to fine tune this model. So generally, that's called the transfer learning concept, and then
Yeah.
you can use this model. Okay, so that's
Yeah.
just the modeling. But then you have to focus on like compressing these models. As I said, applying different techniques for compressing these models.
So, Samy, during this experience, right, you're coming from the world of IoT and you started doing AI and Edge AI a lot. I'm curious to know, what are the things that you've learned during these challenge exactly, right? When working with the Edge AI Foundation and competing with peers working on these models, what are the learnings that you extracted from that experience?
So the first learning is actually so handling like a large volume of training samples. Okay, so there are some difficulties in training these networks. Okay, and the other challenge is actually not exactly the challenge. Actually, we have to understand the basis or the reason for designing these baseline models. Okay, so that's the point that we can focus on so that we can make this model like a more efficient. Okay, So
Yep.
understanding existing models, the rationale behind the architecture of that particular model, and so the some of the hyperparameters that they have used to train and evaluate these models, and handling like a large volume of data, like so 1.3 million is very huge. So you cannot use a simple workstation to process all these things. Really, we need a server to handle all these things. So all of these are some of the learnings from this competition. Okay, and
Right.
also I learned from others. So the other competitors, so they have also proposed very interesting architectures. But unfortunately, there are some discrepancies or there. So their model was not able to do better on the unknown data sets. Maybe the model was doing better on the training data set itself, but completely an unknown data set, they are not able to do it. Okay, so basically there is another concept is actually the generalizability of this model, right? So once you train this model, so it should generalizable, right? So for the camera example, let's say you have collected images of like some 100 different peoples, and you are trained it. So all of a sudden you are having a visitor who is completely unknown to you, right? The
Yep.
model should be able to detect, right? So that's a generalizability aspect of this model. Okay, so that's also I learned as part of this competition.
Nice, nice. And any big haha moment or like, why didn't I think about it? Because usually when you compete against like big other brains, there are this kind of moments where you're just like, oh, that's super smart. So did you see anything, or during your own experiences that really was that kind of a big thing, big haha moment?
Yeah, sure. Actually, so I started with training like a various combination of ways to optimize these models. So, in fact, the winner of this actually the first rank winner. So, as part of
Yeah.
the training, training on the training leaderboard, actually is the leaderboard. So he used some different concept. This is called separable, convolutions. So which is also widely used techniques actually. So because of that, he was able to get like a even much more compression ratio compared to my model. Okay, so I knew these techniques are available, but somehow it slipped from
Yeah.
my mind. So I did not try that. Okay,
Yeah,
yeah,
that's why I love this kind of challenges, because you learn, even if you're one of the experts in that domain, or you know more than a
right.
lot of people out there, you still learn a lot. Cool. Sammy, so I guess people can check out your work and what you've done, right? So you have some GitHub repo or something. So we'll put the link down there,
Yes, sure.
and eventually tell us what would be your recommendation for someone who is in IoT and is starting to do edge AI? What are the like top level 1, 2, 3 things that you would recommend them to do?
Yes, sure. I'll share my experiences and some recommendations on where to start. So before that, the my model architecture and the code base and everything is there in a GitHub repository. So it's
All
also
right,
linked with the AGI competition page, so where people can take a look at and they can enhance it. Okay. So coming
perfect.
to the starting point. Okay, somebody wants to get a better hands-on with AGI. So basically, they have to focus on like a multiple things. So this is a convergence of different fields. Like you have to understand IoT, so embedded system, microcontrollers, and the other side AI models, AI model architectures. Every now and then, new model architectures and everything is keep on coming. So this it really needs like skills from different disciplines. Like as you should have
Yep.
good at handling different hardware systems and then the software systems, so the programming, all those things, right? So if someone new wants to get into this field, I think, as I said, they have to focus on some fundamental courses related to understanding IoT, microcontrollers, embedded system, and programming them, and then the ML side related stuffs. And there is a clear and very interesting converge point. So where they are already training these networks, and then they can focus on learn about all these techniques, so that can be applied to doing efficient models actually. So by
Yep.
the way, this HGI field is keep on increasing. So we see a lot of interest from the community. So industries, it's going to boom.
It is. I agree with you. I said, I think, a few months ago that 2025 will be the year of AGI. I
Right.
stand by this because I believe that it's going to be huge and big. I'm just back from Embedded World in Nuremberg, which is the mecca of anything embedded solutions. And AGI was everywhere. Every single booth had their own AGI demo, and many of them were really good because they were focused on actual use case. They were solving real problems, and they were leveraging existing solutions, but some were homegrown and home built, and it was fascinating, really interesting to me. Samy, thanks again for your time today. I did learn a lot, and I'm fairly sure that our audience learned a lot as well. So I thank you for your time. Congratulations on being one of the winners of this challenge. And well, I hope to see you soon in a round. See
Yeah,
you, man.
sure. Thank you so much. So I would like to also share one last point. So
Yeah,
I'm teaching a course on Edge AI. So the materials and the slides, codes, exercises, and everything is there in the public domain. I'll share that link with you later. So maybe that
awesome.
you can put it. So by the way, this course is actually there are a lot of similar courses are there being taught at different universities and industries. So basically, my course is actually focused on kind of curating the best thing from all these courses and kind of customizing this for like a different students, right? So that's how I'm working on. So I open source all the slides, materials, and everything is
Right.
there. So anybody who wants to take a look at, okay, I'll be really happy to do that. So
Nice.
also I'm,
Well,
I'm planning to conduct a lot of training programs for industries this summer. So anybody wants to do some consultant work or some training program for their industry employees, I'll be happy to do that. So yeah,
awesome. Awesome.
thank you so much.
Yeah, well, thanks for sharing all of these resources. These are not easy to come by, and so it's really interesting to be able to access them, especially freely like that. We appreciate you a lot. Have a good
Yeah.
one, Sammy. Talk to you soon. Bye.
Okay. Thank you so much. Bye bye.